Hello, I am Shashank, and today I am going to present my final project on federated learning. Okay, so start with its definition. Federated learning is a machine learning technique that trains an algorithm across multiple decentralized edge devices. Edge devices may be like a smartphone, or it can be your laptop, or it can be standalone servers also. And with training the models on these server without exchanging data. So in normal machine learning system, what we do is we send the data to the cloud and we train the model on the cloud. In this federated learning, what we send is we download the model and then we train the model using the local data, and then we push the updated weights to the central server where it is aggregated. Yeah, so it's different from normal learning. Is by instead of bringing data to the central device, we share the model and train the model on individual edge devices. Yeah, so this is federated learning. The main work of my final project is dealing with two of the threats in federated learning, which are adversary acting as a client can attack the shared model using poisonous attacks. Here, poisonous attacks means something which will poison the model, and so that its performance gets worsened. And the second type of attack is like a client acting as a adversary acting as a client can steal or de-anonymize the sensitive data through careful observation and isolation of victims model updates. So the some of the data leaks can happen. So these are the two of the threats in federated learning. Now, before going into the work of my final project, I would like to introduce you all to the concept of differential privacy and machine learning. So, differential privacy is a framework for measuring the privacy guarantee provided by an algorithm. And in specifically in terms of machine learning, although concept of differential privacy can be applied to any algorithms which has a database underneath it, but especially applying to machine learning, what it does, it introduces some types of randomness to the algorithm, to the machine learning algorithm, so that the probability of learning a set of parameters remains the same if we change a single training example in the training set. The intuition is that if a single training example cannot change the outcome of the learning, then the specific about that examples cannot be extracted from inspecting the parameters of the model. Like if a single, yeah, so that is the intuition. And we are going to apply this principle in my current final project, and we'll look how it can address those two problems. So the project explains. So the project is about Biscotti system, which is already published, but I wanted to explain it better in like explain it in a more simpler language in my project. And also I wrote a code, like I also uploaded the code on differential privacy. So what is Biscotti? Biscotti is a decentralized blockchain network where node through distributed consensus add new blocks of weight changes to the blockchain network. So what it does is blockchain network is a decentralized system where each block is added through distributed consensus and there is no central authority in it. So each time training a model is basically weight updates for neural networks. So basically what it does, or any other parameters for other machine learning models. So what it does, it updates the weight in each iteration of learning and then push those weight updates to new blocks. So this is how this work. Now nodes are kind of edge devices, as we talked about in federated learning, but they have added responsibility also, which is, and their responsibility is chosen randomly so that there is no that so that the whole system remains fair. So there are two responsibilities for nodes. Those are, apart from training the model, they have two responsibility, which are aggregator and verifier. So verifies the weight updates from peer that calculates the sum of Euclidean distance for each of the updates to the closest r minus f minus 2 updates. and select top r minus f updates with the lowest sum of the Euclidean distance. So what it does, it like if there are f adversaries, then it will filter out those f adversary because the because those are poisonous attacks. So what it will do is like their distance from top r minus f updates would be very large and those would be rejected. So that's how it deals with the poisonous attacks, and verifier plays a crucial role in that. Aggregator. Now, Biscotti uses polynomial commitment along with verifiable secret sharing of individual updates that preserves privacy of the individual update if at least half of the M aggregator participates honestly. I've discussed more about this in the paper, and yeah, and it uses polynomial commitments. Going beyond Biscotti design. In Biscotti designs, weight updates are kept secrets between the peers, but the aggregate of weight are transparent because each block contains it. So as discussed earlier, malicious user can inspect the model to obtain private information, and hence differential private noise must also be added in the training data, which is currently not done in the Biscotti system as it is described in the paper. Although at some other places where the weight updates are shared between the verifiers and peers, differential noise is added, but it's not added in the training example as it's not there in the paper, so that could be done. Yeah, thank you.